You can see people. I can see people getting graphs where their matrix size goes up to like, I think it's 100. You want to say 10,000?
130 something, because I went up to 160.
My laptop complains it can go to 265.
All right, let's get going. Maybe I'll turn on. I'm going to turn on a light so you can see the front a bit better. These lights always suck, so.
Someone has half of them.
There we go. That's not very
It's
good.
20
but-
to the 20. KM is 20, it's coming.
Yeah. That's about as good as I can get.
Wait, I'm caught up in this course, I can understand. It's bringing
It's like 7.
Okay, so how's the midterm? On a scale from, well, I'm not going to do a scale. I'm going to ask who felt really confident, who felt so-so, who felt like they bombed it, who felt confident. So-so. Bombed it. Okay. Yeah, pretty even.
What is your definition of bomb?
I don't know.
Like,
How much C4 are we
below
talking
50?
about?
I don't know. I don't have a definition. I'm mostly interested to see what you think about it, right? About how you did compared to like what you expected, kind of, right?
I did better than I expected.
You did better than you expected? Okay, that's good.
Well, like, I think I did better than
Do
I
you have
expected.
a midterm?
No, I don't know. I don't know what it was. I never saw the midterm.
I was wondering if we could change it up.
Yeah, maybe next week. I'll have to talk to Mihai. I don't know if he wants me to take it up. Sometimes people are a bit picky about that, because they like to reuse them. So, yeah.
We got the midterm. He drew a headline through Dr. Jane Bree.
Yeah.
And scrawled beside it, Dr. Belligan, MD.
Nice.
He is not an MD.
MD. He's not an MD. It's a medical doctor. Yeah.
I redid chemistry too, and I had my old midterm, and it was word for word the exact same thing.
Yeah.
I think I got an 85.
Doesn't surprise me.
Crazy, bro.
That's why we don't give stuff like, or some classes don't give stuff back to you, right?
Yeah.
Because like, yeah,
It's
it's usually the same midterm. Okay, so we're going to talk about change of basis. Yeah, so I want to talk about 3 things. They're sort of tools that you can use, and I'm going to give you 3 of them. First one is, I'm just going to go off my notes because, again, this was like something that I haven't done in a long time, and so I sort of had to go back and relearn it. I haven't done it since I was in this course, so it's not something, change of basis, for me at least, was never anything that I had to use. But say that I have this vector in R3, right? 3, 2, 1, I don't know. And say that I have a basis for R3. How many vectors do I need in a basis for R3? Yeah.
3.
Why?
Because the dimension is 3.
Yeah. Maybe I'll pick this vector. I'm going to keep it consistent with what I wrote here. This, and this. So say that's my basis. You can prove that that's a basis, yeah.
Now, can a basis be anything with just ones and zeros?
It can be anything, pretty much. Like, it doesn't have to have ones and zeros. It could be whatever. The key piece is that the vectors there have to be linearly independent, and they have to span the whole space. So if you take like the span of those 3 vectors, it has to equal the whole vector space. So in this case, R3. But that's it. Yeah, they don't have to have ones and zeros in them. They can be, usually it's nice to pick ones that have ones and zeros, right? Because they're easier to work with, but yeah. So let's say that I wanted to represent, like right now I have this written in terms of, in a way I have this written in terms of like the standard basis, like 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Because they would have like 3 of the 1, 0, zeros, it would have like 2 of the 0, 1 zeros, and 1 of 0, 0, 1. You see that? So what I want to do is I want to turn this, maybe I want to write this in terms of how many of these, how many of these, and how many of these I would need to get this, right? Since this is a basis, I can write any vector using like a linear combination of those, right? A unique linear combination. So what we'll do is we'll say, well, this vector, 3, 2, 1, it's going to equal some alpha 1 times the first vector plus some alpha 2, alpha 2 times the second vector plus alpha 3 times the third vector. Now, when I add these together, so I'll like multiply the A1 in and multiply the A2 in, multiply the A3 in, and then add them into one vector, I'll get that 3, 2, 1 is equal to alpha 1 plus alpha 3, and then alpha 2 plus alpha 3, alpha 1 plus alpha 2. You see how I got that? I did, so for the first entry it was alpha 1 times 1 plus alpha 2 times 0, so no alpha 2s, and then plus alpha 3 times 1, so we get alpha 1 plus alpha 3. Yeah?
How does that equal 3?
So we're just trying to figure out which alphas we can, like what alphas we could pick so that it equals 3, 2, 1, right? Yeah, we're looking for the alphas. So really what we have here is a system of equations from like first linear algebra. You get some alpha 1 plus, maybe I'll leave a space so it's a bit easier to see, equals 3. And then you've got alpha 2 plus alpha 3 is 2, and alpha 1 plus alpha 2 is 1. You've got like a system of linear equations. We can put that into like a matrix form, right? So 1, 0, 1, 0, 1, 1, 1, 1, 0, and then 3, 2, 1. And we could solve that system, right? Using like Gaussian elimination, we row reduce, right? So if we row reduce, I'm not going to go through each step because, I don't know, if you don't know how to row reduce, you can go back and look at your notes. You'll end up getting the identity on this side. I'm using Gauss-Jordan elimination, so we go all the way to RREF. You get 102 as your solution. So what that means is that for me to write V here, I would need to do 1 of this plus 0 of these plus 2 of these. You see how that came about? Okay. So the notation for this is we write V with square brackets around it, and then you write the basis B. So we're writing V in terms of this basis B. And we call this a coordinate vector. And it just has 1 of the first basis vector, 0 of the second, and then 2 of the third. So that's like our coordinate vector for this vector in this basis. It's kind of weird, right? Okay, any questions about this? All good?
It's kind of like changing how you write it.
Yeah, exactly. Because this one, like I said, this is almost in terms of the standard basis, right? There's like 3 of I hat, if you want to call it that, 2 of J hat, 1 of K hat, or E1, E2, E3. And so, yeah, so we're just changing how we write it. Yeah, exactly. All good with that? So there's another way we can go about this, which is what's called so this procedure here is called change of basis. This is like taking a vector and changing its basis. We can do another sort of method to do the same thing, because maybe you don't want to row reduce. Like maybe it's a big system, it's hard to do the row reduction, right? What we'll do is we're going to find what we call a change of basis matrix. So a change of basis matrix is just a matrix that you can multiply any vector by to get it into the new basis. So it's kind of like specific to the basis you're coming from and the basis you're going to. Does that sort of make sense? We usually write it, I mean, there's different notations. I usually write it as I in square brackets, as in like the identity from your, and usually the way, this part's pretty consistent. You write it like this. So if I wanted to change the basis from A to B, you write it like that, from like right to left. It kind of feels backwards, but this is the new basis, this is the old basis. Yeah, it feels wrong, but that's usually how you write it. And sometimes I think your textbook will like get rid of the arrow, so they just write it as BA. I feel like that's confusing, so I'd like to include the arrow there, because then it shows you're going from A to B, right? Yeah. And the arrow's always pointing left. So, how do we come up with this this matrix? I'm going to give you another example. So let's say that we have a say that you have two bases. So maybe we'll work under M 2 by 2. So the set of 2 by 2 matrices. That's a vector space, and I'll give you two bases for it. So one of them is 1, -1, 0, 0. Another one is 1, 1, 0, 0 in this thing. The next vector is 0, 0, 1, -1. And then we'll do 0, -1, 0, -1. So this is a basis for M 2 by 2, right? It's probably not obvious. It's not obvious to me looking at it, but you can go through and show that that's a basis, right? That it's linearly independent and that the span of it is the whole space. Another basis, I'm going to call it B, is, so we can do 1, -2, 1, -2. Let's do 1, 1, -1, 1. 2, -1, 1, -2. And -2, 0, 1, -1. So this is another basis, and again, you can go through and show it. I didn't just come up with that. Yeah, I have that. I got that online. I'm not that smart. So we can write out this matrix where, say we wanted to change any vector that's written in terms of A, like as a basis or as a coordinate vector in A, and we want to change and see what its coordinates would be in B. We can write out this vector, or this matrix. So what we do is we look at each vector in A. I want to make sure I'm getting this right. Sorry, each vector in B, and we write it in terms of the basis A. So we do what we just did, right? We write like the coordinate. So in this case, we're trying to find the coordinate of this vector, if you want to think of it like that. It's a vector, right? In A. So how would we write this vector in terms of these things? How many of each of them would we need? We'll go through the same procedure we just did. And you'll end up getting, let's see what you'll get. 1, 0, 1, 1. So what that means is you would need one of these, plus 0 of these, plus 1 of these, plus 1 of these. And if you do that, you'll get this. Does that make sense? We can go through the next one. Maybe I'll give these names. This one I'll call B1, B2, B3, and B4, so I don't have to write them all out. So if we take the coordinate of B2 in A, I believe you get 0, 1, -1, 0. And if we do the coordinate of B3 in A, we get 1, 1, 1, 1. And last, if we do the coordinate of B4 in A, we get -1, -1, 1, 0. Does that make sense? Yeah.
How did you find these again?
I did them the same way we did like the last thing. So what I would have done is I would have done like set this matrix in here equal to alpha 1 times this plus alpha 2 times this plus alpha 3 times this plus alpha 4 times this. Then bring the alphas in. It would become a system of equations like we did before. And then you just solve it using Gaussian elimination.
How would that system work? I kind of understand it with vectors, but with matrices I can't
Oh,
visualize it.
yeah, no problem. So like if I were to do this first one, it would be this equals, so it's going to be alpha 1 of this, or times this. So we'll have like an alpha 1 in the first spot, and then like a negative alpha 1 in the second spot. Alpha 2 times this, so plus alpha 2 plus alpha 2. Then this one it would be alpha 3 times this. So alpha 3 times 1, alpha 3 negative 1. So we should have alpha 3 and negative alpha 3. And then for this last one, we're just subtracting alpha 4 on each of these. So we get this. And then once you get this set up, right, this is equal to this. So you would get like 1 equals alpha 1 plus alpha 2. This is equal to this. You get -2 equals negative alpha 1 plus alpha 2 minus alpha 4. This equals this, so 1 equals alpha 3, and then this equals this. So -2 equals minus alpha 3 minus alpha 4. So then that's your system. And then you just solve that how you normally would for alpha 1, 2, 3, and 4. Does that make sense?
How did you get the alpha 1 plus alpha 2? And then, yeah.
This one?
Where did alpha 2 come from?
So there was an alpha 1 times this, so that's where I got the alpha 1.
Yeah.
And then the alpha 2 would be here, because it's the second vector.
Oh,
right?
okay, so, okay. And it's only, okay, this makes sense, thank you.
No problem. No problem. Any other questions about it? We good? Cool. So I just sort of skipped all those steps, like solving this, because it would take like 5 minutes for me to do each of them, and I don't really want to do that. So yeah, so we get this, and then we can just write out our matrix. So this matrix I from B to A, what you're going to do is you're going to take, now you have to keep the order right. So this was like B1. You just take the vector that you get out and you put that as the column. So you do 1, 0, 1, 1. B2, we got this, so that's going to go in the second column. 0, 1, minus 1, 0. B3 is all ones, so 1, 1, 1, 1. And B4 is this, so minus 1, 1, 0. So that's your matrix. Now if you multiply that matrix by any vector that is represented in A, so like maybe you have something that's like 4 of these, 2 of these, -1 of these, and I don't know, 7 of these, you could turn it into how many of the B's you would have, like how many B1s, how many B2s, how many B3s, and B4s, just by multiplying this matrix by this vector 4, 2, minus 1, 7. So you would just like multiply it by 4, 2, minus 1, 7, and then whatever you got would be how many B1s, how many B2s, B3s, and B4s. Does that make sense? Cool. So this matrix here, this I, which is just this bit here, it's called the change of basis matrix. Good? Okay. The last thing I want to talk about, this was the second thing of my 3. Last thing is sort of bringing it together. So let's say that we have a transformation, T, a linear transformation, that goes from V to W. So V and W are 2 vector spaces. Good with that? Let's say that A is a basis for V, and let's say B is a basis for W. So we have two vector spaces, each of them has a basis. Maybe it's not like the easy basis, like, you know, there's always like the standard basis, right? Maybe it's like, I don't know, 1, 0, 0, 0 or stuff like that, right? If it was polynomials, you'd have like 1x, x squared, right? Those would be your basis elements in the standard basis. But if you have harder bases to work with, maybe writing out the matrix for this transformation might be hard, right? If it's not the standard. We know how to write it with standard, right? I think we did that last week. You just plug each basis element into the transformation, and whatever you get out, that becomes the columns of your matrix, right? So that's something we know how to find, and maybe we'll denote that method that we did before T, like that, just in square brackets. And if you want to be more specific, really, it's from S to S, like you're staying within that standard basis, just calling that standard basis S. So what we do is we're gonna make something that we call a commutative diagram. So we could do something that's rather hard, which is find the matrix T that goes from, maybe I should write this out a bit better. So this is the basis, A is the basis for V, and B is the basis for W. I don't know if I phrased that wrong, but A is the basis for V, B is the basis for W, right? We could figure out what this T transformation is under the basis A going to the basis W. That's kind of hard, right? Like that's not generally an easy thing to do. What we can do instead is we can kind of go around the block, if you want to think of it like that. We can start by figuring out what the I matrix is, and maybe I should write this a little differently. I'm gonna write these as S to be standard, like the standard basis, which is like 1, 0, 0, 0, 0, 1, 0, 0, stuff like that. First, what you do is you go from from A to that standard basis. So you figure out what that I matrix is, just like we did over there, right? Then you figure out what the transformation is just under the standard basis, which is like what we did a couple weeks ago. And last, you figure out how to go from the standard basis back to B. So you do that matrix, that change of basis matrix. So it's 3 steps, which feels hard. But this step is really hard. If you can figure out what each of these 3 are, you can just multiply those matrices together and it gives you this. This kind of diagram, you'll see this a lot in math. They often just draw like a little loop around in the middle like that. What it means is, so this type of diagram is called a commutative diagram, or a commutivity diagram. What it means is, if I want to get from here to here, I can either go straight there, or I can take any other path that will get me there. So it doesn't matter what path I take to get from V to W here. It doesn't matter, right? So in this case, going all the way around is actually easier because we know how to do this, we know how to do this, and we know how to do this. And so we just multiply them together. Now the order matters when you're multiplying them. So like, if I want to find T from going from A to B, you kind of write it out almost how you would think, I guess. So we want like B to be the leftmost thing, and we want A to be the rightmost thing. So you're gonna do that transformation first, then you're gonna do S to S, and I'm running out of room, so I'm gonna write it below. And you're gonna multiply S to A. So you end up with B on the left, A on the right. Does that make sense? Awesome. Any questions about any of that? I know it was a lot, yeah?
What was the diagram called again?
A commutative diagram. Yeah. Commutative diagram. And it's called that, like maybe you're familiar with the commutative property, which is like the whole like UV equals VU, or U plus V equals V plus U. I think that's how we did it in this course. You good?
Yep.
Awesome. You can like swap the order of things. It's the same thing here. You can kind of like, it doesn't matter what order you do things, right? That's why we call it commutative. It doesn't matter what order you go through or like what path you take, right? It gives you the same thing. All right. I just used up a lot of time, but I really hope that was useful.